going to have your minds blown. It's going to be about hardening TEEs. So I'd like to welcome William Wendt. William Wendt from Oasis. And we do have a substitute speaker today. Guy was not able to make it, so we'll have Alex from SCRT Labs. And Han Yun from Phala, and Harry again from Oasis.
Hi everybody, I'm Will, Ecosystem Growth Manager from Oasis Protocol Foundation. We're going to do a panel on defense in depth for TEs. We're joined by members of the SCRT, Phala, and Oasis team. And I'll just give a brief moment for everyone to introduce themselves. So, Alex?
Yeah, hi again. You have heard me before, CEO of SCRT Labs. I'm substituting for Guy Ziskind, who has done a lot of research in this and knows much more than me, so I apologize if I won't be able to go to technical depth that he would have gone to, but I'll do my best.
Yeah, I'm very glad to be here. I'm Han Yin, the CTO and also the co-founder of the Phala team. Since we have been building TE projects for I think 4 or 5 years, and I lead almost all the development in our team. I'm pretty happy to be here to talk about the security and the pitfalls in building TE projects. Thank you.
And just like with Guy, I'm here again to dig into how do we make this stuff a little bit less in the worst kind of situations, right? That's what it's getting down to, right? So, hi everyone.
And that's Harry, Product Manager of Oasis Protocol. So the first question I would like to ask today is probably a bit of a controversial question. It's regarding what are the pitfalls, what are the weaknesses of TEs today? And what are each of our networks sort of strategies to mitigate those pitfalls? So maybe we go in order. Alex first, and we'll go to Phala, and then we'll go to Harry at Oasis.
Okay, so to me, if I compare all kinds of encryption technologies and compare them to cars, so I would say that TE is like a Volkswagen car that is presumably simple, relatively cheap, and does the job, right? But of course, we understand that as compared to, say, ZKP or FHE technologies that rely on math that is very complicated, but presumably bulletproof, we are all relying on TE, on Intel to do their job well. We know there were issues in the past when TE was broken. So our job is to devise schemes where even if the T is broken, there's no catastrophe, right? So I already mentioned that in SCRT, and I believe in Oasis and others, the worst thing that might happen is the loss of privacy for now. And the mitigations we have are immediate patching and re-encryption of the blockchain. That's for now. But I think that there are some directions for the future to mitigate this. So one is using multiple kinds of enclaves and having some sort of MPC between them so that even if one of them is broken, if the other one is still intact, then nothing is lost. I think there are also schemes where just additional MPC between the TE nodes can solve the problem just in case one node is compromised. So if the others are still intact, then there's no leakage. So that's my understanding. So we have some of that in our development roadmap. These are all items that are not very easy to implement and especially to implement correctly in a scalable manner. But that's my take on mitigation of TE issues. Yeah.
Thank you. Yeah, so I'm going to talk a little bit more technical side. But before that, I say just in case maybe some of the people don't have very deep understanding of what TE is, so 1 minute recap. So TE is a special area in your CPUs, mostly like on Intel CPUs and AMD, and also like ARM. They all have TE solutions. So basically, this is an area. You can put your program into this area. And then this area is guaranteed by the hardware to make it tamper-proof. So by tamper-proof, it actually implies a few things. First, you cannot steal the data running inside, and you cannot manipulate how the program executes. So in this way, most of the properties, if you call something trustless, can be achieved. Because yeah, we talk about trustless, maybe less than decentralization, but after all, the decentralization is meant to achieve trustless, so that you can leave some program running without worrying about some people tamper the information inside or how the program executes. So yeah, this is a very simple recap of TE. So based on that, then we can think about the potential security problem. And among them, the biggest problem is the TE itself is designed by human. And then it could have some problem when in the design. So for example, there is a bug in the TE design, and nobody knows that before. And at some point, maybe just a hacker notice it. That is what Andrew in his talk called the zero-day vulnerability. That means nobody else knows there is a bug, and someone just utilize this bug and probably just compromise everything inside TE. So one thing mentioned by Alex, which is really nice, is if you run the blockchain inside TE, then if the TE is broken, then you lose the confidentiality. That means the secret you store in the TE will be leaked, but the integrity is still protected by the consensus. So I think this is a pretty clever mechanism to ensure the worst case is not like the too bad, right? But on our side, we push it even one step further. We don't run the TE, we don't run the blockchain inside TE. Instead, we run the off-chain computation inside TE. Yeah, so in this case, it will be even more tricky. Like now, we have a blockchain and we have thousands of TEs, and each TE runs their program individually. And if we don't check how the integrity between the TE, then probably one of the TE can be compromised, and nobody even knows that. And to make it worse, sometimes if we just blindly think putting the security key in the TE is okay, and I use this security, this private key to maybe send transaction on Ethereum, then it's not even a problem of privacy, because the integrity of the system is also derived from the privacy guarantee. So this is a very I would say it's a nuance when dealing with TE. We must be really, really careful to make sure integrity, privacy are all taken care. So yeah, this is pretty complex. But yeah, in the last part, I would like to mention a basic like a model to check the security of a TE system. So first of all, the correctness. Of course, we want to make sure if the TE is okay, nothing, the program running in the TE should always produce the correct output. And as long as the TE is not broken, then it can be easily achieved. But on the other hand, even not talking about zero-day vulnerability, there is also another part in security, that is liveness, or in an easier word, make something running on TE unstoppable. So if we dig into that, maybe this is even a harder problem to fix, right? Two cases. One case is, what if you run some program in a single TE, and the single TE just got, like, you just pull the plug out, right? It shut down. Then all the program running inside the TE will just stop, and it lose all your information. But if we want to make sure the program running in the TE will not stop just because a single worker disconnected from the network. Then we need some kind of key management. And in case of secrets, they have a full redundancy. So all the TE has the key. So a single TE is not a single point of failure. And in the paper of Akiden, I'm not sure if this is the correct pronunciation, Akiden actually described a model so that the TE can receive the key from a key management system. So as long as the key management system is not broken, then you can always migrate some workload from one TE to another TE. So this is how it can make sure the program is unstoppable. But even after this solution, this problem is fixed, there's another problem, like the DOS attack. So yeah, that's another level. And if you are interested, then we can talk maybe offline because it's too big to be covered in this discussion.
Awesome, thank you so much.
I just keep thinking about like if you're hardening TEs, I've been reading a lot of like cypherpunk stuff recently. And I'm like, well, can we not just make the servers like explode if they detect a breach or something? Like, let's set fire to the data center if you even try to break out of this, right? I'm not sure how practical that's going to be, but I think like the second best thing I'm thinking of is really compartmentalization. So you may have like physical compartmentalization. So the servers are physically in a secure area. Like you have to drag them out, get past the guys with blocks in the data center. Then you might have like the cryptographics of compartmentalization there. So you have an additional cryptographic protocol that's guaranteed by this extra level of integrity that's offered. And then you have the sort of trust minimization, which is again another type of compartmentalization where you're saying, I'm designing a protocol that even though I may trust trusted enclaves, I'm not going to give them the full information. So it's like you have to protect yourself as a user and a protocol designer from this. And I think this is a sort of pronged approach. So you have to use all of the different possible techniques that are available to you in order to harden any kind of execution tool. So I'm all in favor for making servers explode, but in reality, it's not going to be that.
Awesome. Thank you guys so much for your answers. As expected, the first question was controversial, and everyone had a in-depth explanation. But I think the takeaway here is that all of our organizations are thinking about these sort of edge cases very seriously, and we've all put a lot of thought into them. As Harry said, basically defense in depth is the answer. He said explode the servers. Earlier today, I heard someone give it a take the servers and throw them into space so that they can never be hardware attacked. That might be an answer. But anyway, this is a great initial overview in TEs and just how seriously all of our organizations are taking them. So the next question I have is basically around other privacy preserving technologies. So FHE is the one I'm going to talk about first. And basically my question is, currently there's a lot of hype around FHE, but are we thinking about FHE the right way? Is FHE really secure if there's sort of a centralized key manager, if it's not or better, maybe the better question is, would FHE be improved through collaboration with TEs and multi-party computation? So anyway, I posed the question. Let's go in reverse order this time. Harry, start first, and then we'll come back this way.
So I go back to like IBM like 15 years ago when they were hyping up about FHE, where you can offload your compute into the cloud and they can do all these big computations without knowing what the data is. And the way we've ended up with FHE, like with Phoenix, for example, is where there's still this key manager that encrypts the data for the full homomorphic encryption scheme and then decrypts the result out of that. And I think maybe that might not be the ideal situation, but it's necessary to have these contracts that can resolve conflicts, that can act autonomously, and the alternative is using FHE much more like in a sort of ZK context, where here's my data, you go to compute the proof, and then maybe I can prove some property about the results that is verifiable. So I'm not sure. It's an interesting area, and I'm still following it. But at the moment, it seems to be computationally complex.
Yeah, I'm also not an expert in FEG, but in my understanding, FEG is a really awesome technology, just like ZK. Like ZK, I maybe know more about ZK because if you have something that can be then achieved by ZK, it's almost perfect as long as you have enough budget and the latency is acceptable. I think FEG is kind of like a similar technology, so that you don't really need to rely on like TEE, a single like chip manufactured by some big company. But at the end of the day, I think we need to think about the real world use case. Right? If you are just using some maybe make a game and it's just a temporary secrets or temporary security you need, then I think you don't really want to use some very heavyweight zero knowledge proof or like FHE. But there are also the case. For example, you are dealing with some very maybe moving 10 millions or $1 billion of dollar in some way. I don't know. Maybe on DeFi protocol, then the security is the top priority. And in this case, FHE is a good complementary. On the other hand, I think FHE currently has a problem. If you run FHE, you also need some MPC to manage the key, as mentioned by Harry. And this is a problem in scaling MPC. So yeah, I didn't dig very deep into that, but I think probably TE can also help in this scenario.
For sure.
Yeah, as I understand it, some FHE implementations require also using ZK proofs so that the sender of the data can prove that they really know the plain text, right? Because otherwise somebody could just copy your ciphertext and do it. And also I think TEs might also be used in some stages. Again, I'm not too deep into that, but I think this is one of the examples where multiple privacy technologies in it, plus NPCs, so maybe used in one single implementation. But comparing FHE and TE, and again, for the audience, like my understanding, FHE is like this. I send some encrypted data, and then some computation is happening. So let's say this machine calculates the average of, I send a bunch of numbers that are encrypted, and this FHE thing calculates the average, let's say, or the sum, without seeing the actual data. That's the actual magic, right? That's the magic, because like I send something encrypted, and the calculator does not see the data, but somehow by using this arcane math, it just can still calculate the average, right? And it doesn't know what the average is. It returns it as well in an encrypted state, and only I can get this. So this is very cool, but in fact, the TE in a different way does exactly the same, right? With the only difference that the TE does decrypt the data inside it, does all the calculations, and still returns the encrypted result. So I'd say like the functionalities can be very similar, are very similar. Only in TEs we're using something that, well, I might say engineers or humans created this hardware black box, where in FHE we could poetically say something created by the God or by some higher, some higher truth.
Mathematics.
Exactly. Well, mathematics is kind of, the ultimate truth of, not even the universe, but something that goes, below,
Agreed.
above the universe, right? It's not related to this world at all. So that's the difference, but it comes with a cost, right? It's much more difficult to build, and it takes much more time to compute, and it costs much more, gas, electricity, whatever we're paying it. But yeah, so I think it's important that people understand that the TE that can do exactly the same thing that FHE can only with different security guarantees on one hand, because we're dependent on Intel or other guys. But on the same time, much faster and cheaper, at least for now. At least for now.
Awesome. Thank you guys so much for your insights in this area. If I could summarize, FHE is an amazing technology. It allows for sort of computation to be done based on cryptography in an extremely trustless way. TEs maybe not as trustless, but can achieve close to as high a security as FHE, let's say 90%. But in reality, for FHE to really reach its full potential, it still needs multi-party computation or TEs and other privacy-preserving technologies in order for it to reach that sort of full potential. And so, the limitations there right now are that it's not practical right now on its own, and the TEs serve a purpose even if TEs are not the backbone of the technology. But even if FHE is in Phoenix or in Zama or any of these other FHE-based protocols, TEs still have sort of a place to serve in these privacy-preserving technologies. So my next question, it was originally going to be about multi-party computation, but we only have about 90 minutes left in this session, and a lot of the MPC stuff was already covered in the FHE conversation, so I'm going to move to ORAM. So my question about ORAM was, basically, when it comes to access pattern leaks, where basically validators can insinuate certain aspects of privacy or confidentiality about a particular address or a particular smart contract. What can TEs do to mitigate this, and how much of a concern is it? And maybe even further, what sort of is it actually a concern for a majority of applications that we're running on these TE platforms? And we'll go back the reverse way. So, Alex.
Yeah. So again, maybe a quick explainer to everyone here, right? So what are those side channel attacks? So imagine you have a confidential token, right? And what's a confidential token? Essentially a table saying this address has that much money and that address has, it's just a list, right? So when I'm sending money to you, I'm sending an instruction to this contract. The instructions are encrypted, but then the contract would go to the storage. It might, if it's designed that way, it would read the bytes from the hard disk that belong to that signify my account, and then it would read and then write the bytes that signify your account, and then some clever observer, we have some of them sitting in this room who did that. Essentially, they could understand after a lot of tries and also some replay attacks that you do the same thing multiple times. They can realize who sent money to who, right? Which is not very good. Okay, so this is exactly an example of side channel attacks. So in an application like a confidential token, those, if they're implemented in this very basic way, like you just mentioned, it's not very good. Other applications like, say, a DEX or a confidential NFT or a confidential voting, I'm not sure these side channel attacks can reveal much, really. So I think it depends on the application, right? And the solution to this problem is to try and obfuscate those access patterns, right? So in the example I just gave, one way is to say, okay, so I'll just read all the table of all the addresses, make the change in the balances of the people who are taking part in the transaction, then just add 0 to all the others, re-encrypt them all. So I will just read everything, modify everything, and write everything back to the disk or to the storage, and nobody will know anything. But the problem is that that's very expensive, right? If you have 1 million accounts, it will take forever. So ORAM or other ideas, right, are about just reading not just that particular data point that's being modified, but some subset that would obfuscate the thing. And we actually are thinking about different ways of how to implement it best. There are different ideas of different flavors of this ORAM. Questions are whether to make it like one single layer for all contracts or just implement it in specific contracts. So there's still a discussion on that, but we definitely have that on our roadmap. We want to solve this problem so that people feel much more comfortable in using the network. I must say though, those attacks right now are very, I would say, well, not very expensive. They are expensive, and it's not like anyone can easily do that. You need to have some skill and some time in your hands, and some hardware and software and so on. Actually, that was some of the research done by Andrew and his team, and we value it a lot because it helped us really improve the system and solve the problem.
So yeah, if I may summarize, ORAM is a concern for all of our networks, but it, like Alex said, it's expensive, and it sort of is focused on specific use cases, maybe like send, receive, count balances, things like that, and basically, it's because of how expensive and time-consuming it is. It's only sort of a concern for things that are very high value to attack in terms of the privacy space. We're running out of time, so I'm going to just remind Phala and Oasis that we have about 2 minutes left for each of you. If you guys can go over the sort of question about ORAM in a short time frame.
Sure. I think ORAM is a very generic solution, but I think today's biggest take for me is we should always consider the use case. If this is super critical thing, we always want to add ORAM or whatever we can do to increase the security. But for minier stuff, maybe just we want more performance. So yeah, I would like to give this choice to the developer. And there's also a recent concept called multi-proof. You can even including combining TE, MPC, ZK together in some way or another way. Yeah, the idea is the same.
Thank you very much.
In terms of making it optional, I know at Oasis we're trying to do the spectrum of privacy, but the question really is do we have ORAM as a baseline, so no matter what you do, you have some kind of general guarantees and you just take the cost of it. I've designed a system that has no read-write. It only has the nullifier list, where as long as you don't repeat the transaction again, then you have full anonymity. And there's ways of designing around it, but for most people, to make it as easy as possible, then maybe ORAM is this cost that just has to come with it to make it simple for people. And, yeah.
Awesome. Thank you guys for being very succinct in your message. In at least my opinion, in terms of Oasis, it's a challenge to make the solution generalizable, but it is a goal. And like Harry said, maybe some solutions don't need it, or maybe some solutions will have higher needs for privacy. Perhaps nullifiable, not so much the generalizable version, but a different version of privacy. And I think this is sort of the exciting area we get to play in, is we get to experiment. We get to see what the community decides to do and what sort of catches on, what people are accepting. So we have about 2 minutes left for everybody. If there's any closing thoughts on privacy, technology, on TEs, MPC, FHE, whatever there is, each of you guys about 45 seconds to give some closing thoughts. Please share what you think.
Thank you. So I'm very encouraged that a lot of projects are taking up using TEs, and I think Flashbots is one of the more famous projects in the Ethereum ecosystem, and the fact that they're working with TE is kind of encouraging for all of us, and it kind of gives the technology a better name. I'm sure the TEs are here to stay because they are simple to use, fast, cheap, and provide very good security guarantees. So I think we are working and we chose the right technology for our project, and we'll see it improve and prosper.
Thank you.
Yeah, my closing word is that my prediction of this year is going to be a year of multi-proof instead of only TE or ZK or MPC. One example, I already see a bunch of projects, ZK projects. They feel either ZK itself is very, very complex. They don't want to be exploited by some bugs hidden in their code. This is the same problem as TE, right? And the way they do that is they can actually have an additional TEE proof as well. So you have both ZK proof and TE proof, and if both proof is okay, then it's okay. But there are also other teams, they may be like for 100 blocks, they generate one ZK proof and 99 TE proof just to reduce the latency and reduce the cost. Imagine you are a big layer 1, layer 2, it's okay to produce a ZK proof for every block. But if it's app chain, a game chain, or layer 3, it's not okay to just spend so much money and to run everything inside ZK. So yeah, I think multi-proof will be the mainstream maybe by the end of this year.
I think it's taken a while for people to realize that ZK is not just about privacy, and we still have this sort of like a holdover of whenever you talk about the trusted execution, that means you can keep the data secret, and everyone's minds go straight away to the, ooh, do we want that, So I think with multi-proofs, this is a great area of going, well, this is generic verifiable computation. It's got a different trade-off criteria compared to the other tech, and I think it sits up there among them as being this is a very, very useful tool, and to not take use of it where it makes sense the best, then you're missing out on something. And I just want to see what happens in the next 5 years and how this develops.
Thank you, everybody, for your time for this panel. I think it was a great panel. If I could just add one thought, it's sort of in line with everything you guys have said tonight, but like, in my opinion, the future of privacy and confidential computation in Web3 is not TE, it's not ZK, it's not MPC, it's not FHE. It's finding the right sort of composition of all these technologies together and all future technologies that might emerge. So anyway, I appreciate everyone's time and your insights, and let's continue with the event. Thank you so much.
Thank you.